and it's great to see so many folks from the media interested in what NASA is doing or working really hard to achieve for agriculture here in the Central Valley of California at the World Ag Expo. What an amazing opportunity. I'll start by just saying I'm not new to California. I did come from Washington, D.C. last night, but I was stationed as a Navy pilot at Naval Air Station Point Mugu. I don't know what that was. Test 1, 2. Can you hear me? All right. I was stationed at Naval Air Station Point Mugu, California, in Ventura County. Had the opportunity there to fly E-2 Hawkeyes. While I was there, I spent a lot of my time in the North Arabian Sea on the USS Abraham Lincoln, flying combat missions in Afghanistan initially, and then in the Persian Gulf, flying combat missions in Operation Shock and Awe and Operation Iraqi Freedom. After that, I came out here to the Central Valley of California to Naval Air Station Lemoore, where I had the opportunity to fly F-18 Hornets for the first time, and then went to the Naval Strike and Air Warfare Center, where I got to fly Red Air for a lot of the Top Gun instructors, which was a lot of fun. So I love California. My grandfather was in the Army Air Corps, and he's buried at March Air Force Base down in Riverside, and he's side by side with my grandmother as well there. I want to start by saying, as the NASA administrator, I hear quite frequently about spin-offs from NASA. And overwhelmingly, the ones that people talk to me about as the NASA administrator, they say, oh, NASA, you guys are responsible for Tang or powdered drinks. Well, the reality is we really didn't invent powdered drinks, but certainly we took advantage of powdered drinks. And because of that, we get a lot of credit for it. The other thing I hear about is Velcro, how NASA, invented Velcro, and that's the big contribution of NASA to humanity. But what I'd like to share is something much broader. As critical as Velcro is, don't get me wrong. Something much broader. In agriculture, a lot of us are rural. I come from Tulsa, Oklahoma. I represented the 1st District of Oklahoma in Washington, D.C. as a member of Congress. And I can tell you there's a lot of folks in Oklahoma that are rural. And because of space, we have transformed how we communicate. Dish Network and DirecTV. We talk about internet broadband from space in many parts of the country. If there wasn't internet broadband from space, there would be no broadband at all. And of course, when we think about XM radio, for example, in many parts of the country, you might only get 2 or 3 radio stations, but with XM you can get a lot more. Well, all of these communication technologies were born from this little agency we call NASA. When I say little, I'm talking about less than 0.5% of the federal budget. But it's not just about how we communicate. It's also about how we navigate. Earlier today we were hearing from farmers that use self-driving tractors, which is astonishing. Well, that's precision GPS, a technology that was, again, born from NASA. In this case, it was born from NASA for the purpose of doing precision approaches to airports in an airplane. And of course, I was a beneficiary of that as a Navy pilot. But it also applies to farming. So now farmers can get down to a precision. We're talking about less than an inch precision when it comes to precision farming capability with automatic steering tractors and, in fact, automatic driving tractors. But it's not just the way we communicate, the way we navigate, the way we produce food, which I'm going to talk about today, the way we produce energy in this country, the way we understand and predict weather. I used to represent the state of Oklahoma, and I can tell you, every year I have constituents that died in tornadoes. I care a lot about weather, but guess who else does? Farmers. And when we talk about weather, you get up in the morning, you turn on the TV, you see the green blob on the screen, you know when the weather is going to be over your part of the country. 80% of the data that feeds those numerical weather models comes from satellites built by NASA, operated by NOAA, but built by NASA. The way we understand our changing climate, our changing Earth, again, capabilities developed by NASA. The way we do disaster relief as a country. The way we do national security and defense. And of course, I can tell you as a Navy pilot, I've used over-the-horizon communications a lot in my life. And I will also tell you, this is another important thing, People don't realize how important space is to their everyday lives. We think about banking. Every banking transaction in the United States of America is dependent on a GPS timing signal. No GPS, no banking. We think about the regulation of flows of electricity on the power grid. Again, dependent on a timing signal from GPS. We think about the regulation of data flows on terrestrial wireless networks. Your cell phone, again, dependent on a timing signal from GPS. Space has elevated the lives of everybody in the United States of America and, in fact, all across the world. And that's really what I'm going to talk about today. We have elevated the human condition as this little agency called NASA. Again, less than 1/2% of the federal budget, but we are punching well above our weight as an agency. So today we're going to talk about agriculture. And what is NASA doing with agriculture and how does it apply? Well, let's start with farming in space. People say, well, why is NASA interested in agriculture? Why are you interested in plant science? Well, you can see here, there's a picture of the International Space Station with an astronaut growing plants. The question is why? Well, everything we launch into space has mass, and of course it has volume. Well, plants have mass and volume as well, but so does dirt, and so does water. And what we're trying to do as an agency is reduce the mass and volume so that we can actually do more than we could otherwise do. It's very expensive to launch every ounce out of Earth's gravity well. So when we travel in space, we really want to get to a point where we can do agriculture, where we can actually grow food without soil and a minimum amount of water. That's the objective. And of course, we're doing that right now on the International Space Station with a program we call Veggie. Our astronauts right now are growing plants that they can eat on the International Space Station. And of course, we have an eye for what looks like science fiction there on the right side of the screen. We have an eye for Mars. Here's the thing about Mars. It's not like going to the moon. The moon is always with the Earth. Wherever you are around the sun, the moon is with us. We're in the same orbit. We're part of a system, the Earth-Moon system. Mars, however, is in its own orbit around the sun. And the Earth and Mars are only on the same side of the sun once every 26 months. Which means, when we get to Mars, guess what? We're going to stay. You're going to be there for 26 months before we have an opportunity to come home. Which means we have to be able to utilize the resources of another world in order to work and live for a sustained period of time. Plant science is critical for NASA. And I know there's young people here at this show. I saw the Future Farmers of America, the state leadership of the Future Farmers of America here. I saw a number of scholarship recipients earlier today, and I can tell you those scholarship recipients have an opportunity, being what they're about to study, to actually support space exploration with what they study in college, and of course, one even said interested in a PhD. So really, this is what NASA is interested in down the road. We're talking about farming in space. Another question is, what are we doing with space technology to help us right here, right now, today, on the only planet that we know hosts life, although we think that could change in the near future, the only planet that we know to host life, Earth. Well, right here in the Central Valley of California, a lot of folks are familiar with the big challenge we have for competition for water. And of course, when I was here doing my training at Naval Air Station Lemoore, this was a big issue then, and I understand it's as big today as it was back then. There's a competition for resources. The demand is growing. And of course, it's agriculture, and it's endangered species, and it's conservationists that are looking for recreational opportunities for fishing, and it's hydropower, a renewable energy supply that is important to the energy mix in the United States of America. And of course, drinking water to the population centers that consume a lot of the water. We're talking about San Francisco, Los Angeles, San Diego. Drinking water is critically important. That's the demand side, and there's a lot of demand. But guess what? They're not making any more water. But there's a lot more demand. The demand is growing. And it's not just growing for the water, it's going to be growing for the food as well. And here at the Ag Expo, it's important for us to understand how we're going to help manage that water supply. Down in the bottom left, you can see the picture of the flood. So all of the people that are trying to meet the demand for all of the water, they need full reservoirs. That's what they need. But then there's people that are trying to manage floods, and what they need is empty reservoirs. So this puts us in a competing interest kind of position. And ultimately, we have to be able to manage this very scarce resource, very precious resource, in a very responsible way. And it's becoming more and more difficult. But NASA has some capabilities and some technologies that we're going to exploit in order to help water managers be able to predict water in a better way. And I'm talking about snowpack in the Sierra Nevada. When we walk outside those doors, we're looking at the beautiful mountain range of the Sierra Nevada mountains. Well, a third of the water that California uses comes from that snowpack. NASA has some very unique technologies that we can use to measure that snowpack and then convert the snowpack into a water equivalent. How much water is up there in the mountains? And then we have another technology that we're going to take advantage of. It's going to tell us how fast the snow is melting, because how fast it melts determines the magnitude of the water that the water managers are going to receive. And the idea here is to make sure that we're not wasting any water. That's the ultimate objective. So in order to take advantage of the capabilities, we're going to go to technology that NASA developed really for the moon and for Mars. Apollo 15, 1971, our astronauts landed on the surface of the moon for the 4th time in human history. The number 7 and number 8 astronauts on the surface of the moon, but there was a command module orbiting the moon. And what it was doing is it was using a technology called LIDAR, light detection and ranging. Think of radar, except using light instead of radio waves. And what they were doing is they were mapping the moon for the first time in 1971. And of course, we have advanced that technology significantly, and we're doing it even more, and we're getting very precise elevations all over the moon to where it's now fully mapped. We've done the same thing at Mars, and of course, we can actually apply that technology to Earth. So we use LIDAR, light detection and ranging, and what we're doing is we're measuring the mountains before the snow, then we're measuring the mountains after the snow. And we can get really precise measurements of how much snow is in the Sierra Nevada mountains. Now, we're not doing this with an orbiter the way we do it at Mars and at the moon. We're doing it with an airplane. But again, we want to convert the snowpack into its water equivalent so that we know in the spring and the summer precisely how much water is going to come down the mountain. Then we're going to use another NASA technology that we use all the time, a spectrometer. Spectroscopy, what that says is we're going to have the light come off the snow. It's going to bounce off the snow. And when the light bounces off the snow, we're going to split that light into 100 different colors. And based on the colors that show up, we're going to be able to determine how much light the snow is absorbing and how much light the snow is reflecting. Sometimes the snow reflects 90% of the light and only absorbs 10%. Other times, it absorbs 70% based on the color of the snow. Yeah, it's true. Snow has different colors. Depending on the particulates in the atmosphere and how much pollution there is and all these other kind of things, snow has different colors, and it can either absorb 70% or down to 10% of the light. That's how we figure out how fast the snow is going to come down the mountains. And we do this in an airplane that we call the Airborne Snow Observatory. So we've got really impressive scientists that are using this now for a period of 5 years. We're going to watch a video here from some of NASA's best scientists.
For the past 5 winters, science crews have been taking flight over the Sierra with a groundbreaking mission in mind. Using infrared radar to map and decode California's snowpack, how much is there, how soon it will melt. A pilot program in a time of climate change aimed at better management of the state's often uncertain water supplies.
It's enormously accurate, yeah. Even far exceeding what our expectations were going to be with the with the lasers, we're touching every square meter of snow. So it's wall to wall. All the pixels of that snowpack are lit up.
Tom Painter is the principal scientist driving what's called the Airborne Snow Observatory, developed by the NASA Jet Propulsion Laboratory in Southern California. It's technology, he says, that was used to search for water on planets like Mars, now with a more earthbound purpose.
About 80% of what falls onto the state of California comes in the form of snow. So being able to quantify that from year to year is absolutely key.
The Friant Water Authority, which delivers water to 1 million acres of Central Valley farmland, helps pay for the pilot program, which provides valuable insight into how to manage water supplies and helps growers make key crop decisions.
The beauty of this snow survey is that we have a more accurate scientific knowledge of what's existing in the freezer.
The freezer is the Sierra snowpack, which provides up to 1/3 of the state's water as it melts through the spring and summer months. For decades, the state has performed manual snow surveys, which are limited in scope and accuracy.
90.
Frank Gerke, who oversees snow surveys for the Department of Water Resources, says the NASA JPL program is a game changer.
We are a huge fan. It will, over time, revolutionize how we make our forecasts.
It means more efficient operation of reservoirs, hydroelectric plants, and environmental projects like fishery protection. Without a clear picture provided by this NASA program, supporters say, California's ability to manage its own future remains as unpredictable as the snowfall itself.
So that's a little bit about the Airborne Snow Observatory. What I'd like to share with you, though, is we can take this same technology, LiDAR, just like we use at the moon, just like we use at Mars, and of course now we're using it in the air over the Sierra Nevada mountains. But we can also use it in space around the Earth. And we've got 2 specific programs that are doing that right now, although for different purposes. Not to measure the snowpack in the Sierra Nevada mountains as the Airborne Snow Observatory, but instead we have ICESat-2. And what is ICESat-2? Again, it's a LiDAR, laser detection and ranging. And what it's doing is it's in a polar orbit, so it goes north to south, and it's measuring the thickness of the polar ice caps. It's also measuring glaciers and other ice around the world for the purpose of understanding how fast are those glaciers shrinking in the summertime and how fast do they grow in the wintertime, and what is the net value. And what we know now, of course, is that the glaciers are shrinking, but certainly the ice caps are as well. And ICESat launched in 2018, just last year, with LiDAR for the purpose of getting those measurements. Here's the interesting thing, though. It could also get measurements for snowpack if we wanted to use it in that way. It wouldn't be nearly as precise as flying a low and slow airplane. The physics wouldn't allow it to be as precise. But if we wanted to launch additional satellites for that purpose, it is possible. But there's a lot of testing and a lot of things we can learn from ICESat-2. The other satellite that we launched last year actually is a hosted payload. It rides on the International Space Station. And of course, that satellite is, or I should say the payload is called JEDI. And of course, it uses LiDAR as well. It's not there to measure the polar ice caps because the International Space Station doesn't go over the polar ice caps. But what it does is it measures vegetation. It's measuring ecology. It's measuring ecosystems. It's really an instrument that we're using to understand the carbon cycle, specifically carbon dioxide in the Earth's atmosphere. So here's what we know. We as humans are putting more carbon dioxide into the atmosphere than at any point in human history. And there is more carbon dioxide in the atmosphere now than in recorded history. That is absolutely 100% true. What is also true is that there's not as much up there as what we're putting. So the question is, where is it going? So we have these carbon sources, but we also have carbon sinks. What JEDI is trying to do is understand the vegetation. Certain parts of the earth right now are greening. Carbon dioxide is, as you know, farmers, carbon dioxide is plant food. A lot of parts of the earth right now are greening in ways that we're trying to understand. So we can understand how the atmosphere and the biosphere and the hydrosphere, phytoplankton in the ocean, we're trying to figure out ultimately how all of this carbon cycle works. And that's our job at NASA, is to make these determinations. But I also want to be clear, what is the instrument? It's a LiDAR. It's on the International Space Station. The International Space Station is human-tended, which means we could actually do modifications on it if we wanted and things like that. So it's important to recognize the International Space Station is actually doing great work here with LiDAR, and we can use it to measure ice and or snowpack, although we haven't done that yet. It is certainly within the realm of possibility. Again, when you do it from space, it won't be nearly as accurate as if you do it low and slow from an airplane. But again, we could launch a lot of different LiDARs into different orbits and measure all kinds of water ice as necessary. Okay, my point here is this. NASA is working really hard with our partners, specifically the state of California Department of Water Resources, to make sure that they have all the data that they need to make really good decisions, or at least less bad decisions. And I know it's a very contentious issue here in the state of California. But let's get down, instead of thinking about water management in its entirety, let's get down to specific farms and how NASA is helping specific farms. So here is a picture. You can see the device, the second picture from the left. That's just a ground weather station. It's collecting all kinds of information on weather. And of course, it's operated by NOAA and the state of California, and it's helping farmers understand what we call evapotranspiration, which farmers here in California, farmers who farm in arid environments, understand evapotranspiration. It's a measurement of how much the plant is transpiring, how much water is it putting into the atmosphere, water vapor into the atmosphere, and at the same time, how much water in the soil is evaporating. So you take evaporation and transpiration, and you can come up with an amount of water that is being used, and then you can calculate from that very precise measurements for an irrigation plan. That's ultimately what those sensors do. And here in the state of California, they're used quite regularly. One of the challenges is they can only get that evapotranspiration measurement down to 1 1/4 square miles. Well, that might not be specific enough for many farmers across the state of Oklahoma. 1 1/4 square miles seems like not very much, but if you're growing a specific crop on a specific side of a hill with a specific side of a kind of soil, it might not be the right measurement, and it could actually make you reduce your crop yield, not increase your crop yield, depending on how it's used. So what NASA is doing is we're using our satellites. You can see on the left there, we've got a USGS satellite, the Geological Survey, the Landsat satellite, which is measuring the Earth in both electro-optical and infrared. And we've got other satellites, Terra and Aqua. And of course, the European Space Agency is also providing data to this calculation. So what are these satellites doing? They are measuring, parts of the electromagnetic spectrum coming from the Earth. In some cases, they're passive detection. In other words, they're measuring in IR, the heat signature coming from the surface of the Earth. In other cases, it's active. In other words, they're sending either a microwave or a radio wave or even a light wave, as you saw with LiDAR. They're sending signals down and receiving those signals back. And what we can do with a partnership with the University of California, the Cooperative Extension, we are able to take that evapotranspiration measurement, and instead of being at 1 1/4 square miles, we're actually down now to 1/4 of an acre, which is a much more precise and accurate measurement for evapotranspiration to help farmers ultimately understand how to precisely irrigate for their crops. Now here's the important thing to note. I want to be clear. We are not doing this all over the United States of America. This is a pilot program in partnership with the University of California, in partnership with the California Water Resources, in partnership with NOAA and USGS, Geological Survey, and NASA. So in this partnership, we're using our data, combining it with all the other data, and what we're getting from the Cooperative Extension from the University of California is some very good software tools where we can take this data and apply it down to 1/4 of an acre scale. And that's what that third row is, crop manage, which is University of California Cooperative Extension, plus NASA data, and we're going to actually create data that's available for somebody's iPhone, for your mobile phone. We're going to get it down to 1/4 of an acre for somebody's iPhone, so you know precisely how much to irrigate in your particular patch of your farm. The interesting thing here, it says training the next generation. This is why universities are so important. It's why NASA is so important. The demand for food is going to go up. The demand for the water that we need to grow that food is going up at the same time. The resources are not growing, but what we can do is we can very precisely measure, and that's our goal, very precisely measure so that we can come to a day where we can actually, as the population grows, as the demand grows, we're going to be able to feed more of the world than ever before. Again, this is a pilot program here in the Central Valley of California. So here are some of the results, and these are pretty amazing. Reduced water use by 20% for a whole range of vegetables. That's an amazing result. Reduced nitrate leaching by up to 50%. In other words, the soil retains its nutrients because you're not overwatering. You don't water so much, those water-soluble nutrients stay in the soil and your plants actually do better. So by reducing water and reducing nitrate leaching, we're actually sustaining crop yields and quality, for less water. Here's the thing, the bottom line there, NASA is working to expand these tools. We want to prove the capability, prove the technology, and then expand it to broader regions and ultimately to the entire United States. And we're going to talk about that here in a second. Here's an example of how NASA is partnering with a very specific private company in a public-private partnership to test out our satellite data in all parts of the electromagnetic spectrum. And what we're finding here, you guys are probably familiar with Gallo wines. What we're finding here, and this comes from them, based on their direct cooperation, NASA and the vineyard, we're finding that they're able to reduce their water consumption by 25%, which is again astonishing, without losing any quality for their grapes. NASA is also funding the Desert Research Institute. Think about that pilot program that we have right here in Central California, the Central Valley. Well, here's a program that we're funding that's trying to get that at a much broader scale. We're talking about 8 states in the western part of the United States. So we're funding the Desert Research Institute in order to broaden that evapotranspiration measurement to get more data to more farmers when and where they need it. Now, in this case, because we're broadening it so far so fast, we're not getting down to that quarter acre scale, but what we can do is we can help water managers in these states better allocate the scarce resource that is their water supply. We also have a new tool for this particular program. We launched it last year. It's attached to the International Space Station, and it's called Ecostress. We talked about LiDAR, shooting a photon of light and measuring it back and measuring elevation from that photon of light. Well, here, Ecostress is passively detecting plants in infrared from the International Space Station. When I say infrared, what does that mean? We're measuring heat. We're measuring the heat from plants. Why would we want to do that? Well, as water goes up from the roots of the plant, through the stem to the leaves, it transpires. The plant transpires. The stomata in the leaves actually breathe, and that water vapor is released into the atmosphere. Well, if that plant feels stress, I know I'm talking to agricultural experts about stomata, but bear with me, because there's a lot of people watching online that might not know. Know this, that when the plant feels stress because it doesn't have enough water, the stomata close, and the plant's heat actually goes up, and we can measure that from space and detect well ahead of time how much stress the plants have. In some cases, we can detect 2 weeks earlier than what you can detect with the human eye, and we can mitigate the effects of plant stress before they become a big burden. So we're trying to determine water stress on plants long before visual detection. Here's another video.
We're interested in our ability to sustain food production. We're interested in our ecosystem health, and that's all tied to water. How much water our plants, our crops need, we want to know. And as water resources become more uncertain, more variable, we need to really track that really precisely. We can't just guess anymore.
So Ecostress is going to measure the surface temperature, and then we're going to use that surface temperature to be able to determine how much water the plants that we're looking at are using.
We'd like to show how we can use Ecostress data to optimize agricultural water use.
Ecostress is an instrument that's going to go on the International Space Station. It stands for the Ecosystem Spaceborne Thermal Radiometer Experiment on Space Station.
It focuses on how much water plants use all over the planet and how much water plants need, and if there's stress, water stress or heat stress, that plants are facing.
We can measure the surface temperature of the Earth within a few tenths of a degree, and then we can use that information to look at objects on the surface of the Earth, and in this particular case we're interested in looking at plants.
Plants, as they start to suffer from heat or water stress, they begin to heat up. In a similar way to a human with a fever, we can pick up that stress before the plant is visibly affected. So there's this window where water resource management and agricultural users can actually allocate more water before they die, before the damage is irreparable.
The space station is going to fly over at different times to be able to look at how the stress is changing through the day and allow us to characterize vegetation in ways that we've never been able to characterize it before. The instrument itself is looking down at the surface of the Earth, and it uses a mirror that rotates to scan across the surface. This measurement is being made in microseconds, but it's enough time for us to measure the energy that's coming off it and then translate that energy into a temperature.
The temperature measurements from Ecostress can detect volcanoes. We can detect urban heat from cities.
So although we're focused primarily on looking at plants and making sure that we can maximize the amount of food that we can get back for the water that we use, the mission can be used for many other purposes. What hasn't been possible in the past is to make the measurements as frequently as we need to make them with sufficient detail, and it's that combination that is so important. And really that's just a reflection of the improvements in technology.
Our ability to sustain livelihoods, food production, ecosystems, and health of the planet through Ecostress data is invaluable.
So one thing I want to share with you, the important thing about Ecostress, again, it's on the International Space Station. So what does that mean? That means, again, we have this amazing tool for humanity that is tended by humans, that has its own power sources, that has its own, well, not its own, but it does have propulsion. It will be there for many years, and we can attach all kinds of instruments to it. You can see in the top right corner, you can see what's called the Japanese Experiment Module, GEM, which is where Ecostress is attached as one of those boxes. You see those shoebox looking things on the GEM there. I will tell you, those aren't exactly shoeboxes. They're the size of maybe a pretty big desk, as a matter of fact. So just want to make sure people are aware how the International Space Station plays in a lot of these experiments. And you can see there's a lot of experiments attached to the International Space Station. This, of course, is not the only one. The end goal here is, what we're looking for is open ET, is what we call it, evapotranspiration. We want the entire United States of America to be able to go to a website and find out what the evapotranspiration number is for their 1/4 of an acre in their part of the country, and be able to very precisely measure how much water their plants need and supply that exact amount. Not too much, because again, you'll have those nitrates disappear, and not enough, because then you'll have distress on the plant. So the goal here is open ET, open evapotranspiration for the entire United States of America. Now there's one other technology that I think is really neat that we're able to take advantage of now for agriculture. We call it GRACE. What GRACE is, it's a gravity recovery and climate experiment. GRACE. Now, This is mind-boggling, but I'm gonna do what I can to explain how it works. And of course, everybody's gonna correct me back at the Jet Propulsion Laboratory, but that's okay. Imagine, when you think about gravity, it is commensurate with the mass of a planetary body. So the moon has less gravity than the Earth because it has less mass. And Mars has more gravity than the moon, but less gravity than the Earth because it has more mass than the moon and less gravity than the Earth. And of course, when you think about the sun, a whole lot of gravity. And when you think about a black hole or a supermassive black hole, we're talking about so much gravity that even light can't escape that amount of gravity. So when we think about gravity, think about mass. So what we've done here with GRACE is we have two satellites, you can see them in the picture, following each other, and between them is a LiDAR, light detection and ranging, and it very precisely measures how far one satellite is from the other satellite as they follow each other around the Earth in orbit. Now what happens is the Earth's mass is not uniform, and therefore its gravity is also not uniform. And you can see that when these little satellites pass over a mountain range, maybe the Sierra Nevadas, what you'll find is that the satellite in the lead actually starts moving ahead of the satellite behind. Why? Because the gravity is pulling it. As it falls around the Earth, the mountain range over here is pulling it faster. And then what you'll find is the satellite behind will catch up to the satellite ahead. And what you can do is you can very precisely measure the gravity of planet Earth, which is not uniform. And you can see where the mountains are and where the valleys are by measuring the gravity. But here's the thing. There are some parts of the Earth where the gravity is in excess of the mountains. There's no mountains there, but there's a lot more gravity. And then what we're finding is that the gravity is changing. The gravity of the Earth is actually always changing as the Earth changes. How is that possible? Well, it's possible because of the water in the soil. We're talking about ground soil down to 10 feet deep. We're measuring how much gravity there is based on water in the soil, if you can imagine that, and it's proving to be very, very accurate. What's even more amazing is it's not just the ground soil, but it's the water underground. We can see that aquifers are being depleted, and we can see when aquifers are being replenished. We can see all of that with this mighty little device called GRACE, which is proving to be very, very capable in understanding, predicting, forecasting drought. So the National Drought Mitigation Center in Lincoln, Nebraska is now using GRACE data to very accurately and precisely measure where the drought is, when it starts, when it ends, and ultimately make these predictions, which is critically important. Now, why do we want to make predictions? This is not just for farmers, it's for policymakers. When there's people that need support, we need to get it to them ahead of time, not after time. Ahead of time, not afterwards, I should say. So that's what GRACE is, and it's being used for a drought indicator, which is a very powerful tool that's being used by the National Drought Mitigation Center. Matt, can you move that forward? Oh, here it is. So here's a perfect example of, oh, there we go. This is the last, I got 2 more slides here that are left. I wanted to put a slide in here. Look, we talked a lot about sensing the Earth from space and trying to use that data to enhance agriculture. Right now, we're doing it at small scale. We're doing it, of course, with the University of California Cooperative Extension here in the Central Valley. We're doing it with grapes, again, here in California. We're doing it at a large scale with 8 Western states. But again, the goal is to make it much bigger than that. But right now, these are all just kind of pilot programs, test programs. But I wanted to share with you some of the things that NASA's been involved in agricultural-wise throughout history. So chlorophyll meters to help us understand the health of our plants. Chlorophyll meters, it's using a sensor technology that was developed by NASA. We talked a little bit about automatic tractor steering and driverless tractors. At this point in the United States of America, 60 to 70% of the farmland is farmed with automatic steering from precision GPS, which again was a NASA technology created for the FAA to help pilots precision navigate to shoot precision approaches using GPS. We talk about air purifiers to preserve produce, both on the trucks to get to the store and even within the grocery markets. Grocery stores are actually putting these purifiers into their air conditioning units so that produce stays fresh longer. And of course, drones. Drones are really making a big impact on agriculture now. And there's a lot of different ways that drones are being used. The delivery of fertilizer, the delivery of pesticides, imaging for crop health, multispectral imaging to figure out what the crop health is, irrigation performance, even planting from drones, and livestock monitoring. What NASA is doing right now with drones is we are trying to figure out how to integrate unmanned aerial systems into the national airspace system. So then you can fly your drones beyond line of sight, over the horizon. For folks that have big farms, you lose contact with your drone, and guess what? You're in violation of the law. Well, in this particular case, what we're trying to do is enable you to fly your drone beyond line of sight, even with satellite communication technology, in a way that will save you time and money, and get you more data and better data for your farms. And all that technology is being developed by NASA. I shouldn't say the technology. What we're trying to do is figure out what the system is that enables it to happen without putting anybody in danger. And then, of course, you see there leaf sensors that will actually measure certain nutrients that your plant has, the amount of water in your plant, and then those leaf sensors will send you an email. Again, technology developed, sensor technology developed by NASA. And this is my last slide. This is really what it's all about. I mentioned earlier that it's really not just about responding. It's about getting ahead of the issue. And here's a quote from Uganda where NASA technology actually saved lives and it saved money. So instead of having to come in with aid after a catastrophe, we can actually mitigate the catastrophe, prevent it from happening, and save U.S. aid dollars, and at the same time save lives and money in foreign countries. So here's the quote. In the past, this is from the office of the Prime Minister in Uganda. In the past, we always reacted to crop failure, spending billions of shillings to provide food aid in the region. 2017 was the first time we acted proactively because we had clear evidence from satellite data very early in the season. Friends, that's what it's all about. How can we save lives? How can we grow more food? How can we ultimately feed more people around the world, save water resources, and do it in a way that maximizes the utility for everybody, not just in the country, but in the world? And these are some of the things that NASA is currently working on. I want to stop by saying, again, we are a small agency. We didn't get into this business because we were interested in agriculture. But because of what we're doing for a whole host of other reasons, we can actually benefit agriculture. And through partnerships with universities and states, we're actually able to make a difference. And we want to continue doing that. As the NASA administrator, I will be doing that as much as I can, so that every piece of the technology we develop ultimately gets fed into its best uses for all of humanity. So with that, I want to thank you for having me. It's been awesome being here. I'm gonna bring up Jamie Johansson now with the California Farm Bureau. Let him say a few words. And before we end, I have one more video that I'd like to play. It's not about agriculture. It's about going to the moon. The President has issued Space Policy Directive 1, which says we're going to the moon, and we're going sustainably. In other words, we're going to stay. I'm going to talk about that for 2 minutes and then show a video after Jamie's done. Jamie?